Hello everybody, myself Jyoti, and today we are going to start with the new series of lectures based on nuclear energy, where we will discuss about nuclear fission, nuclear fusion, and so on. Before attending this lecture, if you can go through my lecture on Weizsäcker's semi-empirical mass formula, it will become a little bit easier for you to understand this topic. Okay, so let's begin. So first thing is, what is nuclear fission? Horn and Strassmann in 1938 concluded that when uranium it is bombarded with neutrons, the uranium nucleus it splits into medium atomic mass nuclei. And generally, the common reaction is since barium and krypton they are formed. So this type of disintegration in which a heavy nucleus splits up into two medium mass nuclei of comparable masses. Because see, sometimes what we have a nucleus which is emitting proton, neutron or some particle, and we get another nucleus. So in that case also we can call it as a fission, like breaking is taking place between one proton is formed and another nucleus is also formed, daughter nucleus. But there we are not calling that reaction as a nuclear fission. So basic difference is here when we are talking about nuclear fission, when a heavy nucleus breaks we get two parts. One part is not very small and another part very big. Both the nuclei which are formed they have comparable atomic masses, then we call it as a nuclear fission reaction. Now, neutron induced fission. So, we can accelerate this process of nuclear fission by means of neutron capture. But still, all heavy nuclei they do not undergo fission when bombarded by slow thermal neutrons. But we can do this process that when we accelerate the process of fission by bombarding it with neutrons, then that is called as neutron induced fission. And here the neutrons which we use they should have a thermal energy, they should be slow, the neutrons shouldn't be fast moving neutrons. The one important question which arises here is why uranium 235, an isotope of uranium with only 0.7% abundance, will undergo fission if it captures a neutron, whereas uranium 238 will not undergo fission if it captures a neutron. We have uranium 235 isotope of uranium, uranium 238 isotope of uranium. Uranium 235 when it captures a neutron it undergoes fission, but uranium 238 when it captures a neutron it doesn't undergo fission reaction. So why this is happening, that is the question which we have to answer. Now all of you must be aware of the binding energy per nucleon against atomic mass number curve. So when we there is one lecture which is there in nuclear physics series which is based on this also. So you, if you have a difficulty in understanding binding energy per nucleon versus atomic mass curve, then you should attend that lecture also, because it is very important concept in nuclear physics. So from the binding energy per nucleon against atomic mass number curve, we know that binding energy per nucleon in the uranium region, it is about 7 MeV. So binding energy per nucleon for stable nuclei, it is of the order of 8. It is highest for iron with 8.7 MeV. It is lowest for lighter nuclei and it is lowest for heavier nuclei. So we know that uranium, it is heavier nucleus, so naturally it is not stable, and its binding energy per nucleon it is not equals to 8 MeV, it is around 7 MeV. And this energy per nucleon it is almost equal to height of the potential barrier opposing fission. So if in a nuclear reaction, if in a uranium fission reaction has to take place, then there is a potential barrier of 7 MeV which has to be crossed. Understand the point that if in uranium we want nuclear fission reaction to take place, then there is a potential barrier of height 7 MeV and that we have to cross. So now when a neutron is added to the nucleus of uranium 235, and even nuclide uranium 236 is formed. So we know that uranium it has atomic number 92. Now as it has captured one neutron, when it captures one neutron, neutron doesn't carry any charge, so uranium 92 it will be there. And as neutron has atomic mass number 1, so naturally uranium 235 will convert to uranium 236. Uranium 236 has mass number E1 and atomic number 92, that is even. So it is even nuclide. The pairing energy term, now that is how I was asking you to go through Weizsäcker's semi-empirical mass formula. So what is Weizsäcker's semi-empirical mass formula? I will just give an introduction. So Weizsäcker's semi-empirical mass formula, it calculates binding energy, and it says that binding energy, it consists of asymmetric energy, volume energy, surface energy, pairing energy, and so on. So one of the term which contributes to binding energy, that is pairing energy. So the pairing term in Weizsäcker's semi-empirical mass formula, that value if you calculate, it comes around 0.6 MeV. So for even nucleus, the pairing energy term, it is 0.6 MeV. As in uranium 235 we are getting even nuclide, so we will have that pairing energy term in the Weizsäcker semi-empirical mass formula, and the total energy, it will become 7 MeV plus 0.6 MeV because of pairing energy term. So total energy will be 7.6 MeV when uranium 236 is formed. Now for crossing the potential barrier for fission, we need only 7 MeV. And here, how much is available? 7.6 MeV. So to cross the potential barrier for fission, 7 MeV is required. We have 7.6 MeV in case of uranium 236, and that is how uranium 235 can undergo fission by neutron capture. Now let us consider the case of uranium 238. When uranium 238 it captures one neutron, naturally its atomic mass number will increase by 1 unit, so it will become uranium 92 239. Now when we talk about uranium 92 239, atomic number is 92 and atomic mass number is 239. So 239 is odd number. So this nucleus which is formed in case of uranium 238, it is odd even nucleus. And whenever you have an odd even nucleus, the contribution of pairing energy term is 0. When the nucleus is even, then pairing energy term value which is there, it is 0.6 MeV, which was there in case of uranium 236. But here when uranium 239 is formed, that value 0.6 MeV will not be available. That is how the potential barrier, it is of the order of 7 MeV. If we have to cross, we need that 0.6 MeV, which is not available, and that is how uranium 238, it does not undergo fission reaction, but uranium 235, it undergoes nuclear fission reaction. So this is a very important concept in nuclear physics. Thank you. Thank you so much.